Hello, this is Sean Pearce again. I'm going to talk to you a little bit about polymers today. So let's get on and start working through the PowerPoint. Apologies, it's all PowerPoint. If there is a more groovy way of sort of delivering the lessons, I will go to it. But what we're going to be talking about is how we end up from getting one of these and sticking them all together into a long chain. That is called polymerisation. It goes from this first, there we go. It goes from this sort of first bit here, those ethene molecules, and makes this polythene. So we're going to be talking about that. And these are the things I'm hoping you will be able to achieve by the end of the lesson. And that's looking and describing polymerisation in alkenes, making sure that you can identify the repeat units, identifying the monomer that actually makes these things, and then we're going to talk about the environmental sustainability of what we're doing. Some really, really important stuff, and to be fair, it's stuff that's actually relevant to your daily lives. I've got a pen here, I'm sitting on a chair, I've probably got some form of polyester in my shirt, so polymerisation and polymers are around us all the time. I'm currently drinking water from this bottle here, which is probably made from, let's have a quick look, something very unsustainable, so I'll be reusing this bottle. But it's all made from polymers, so really, really important things. We're going to be talking about what biodegradable and what photodegradable actually mean as well. And that's really, really important to understand. And it's where polymers are going to be moving in the future because of the sustainability issue. So there are some key words to do with this. We will be going through those keywords as we go through the lesson, but I am going to pop the definitions up. If you need to, always feel free to copy the definitions down, pausing the video as you go. And in fact, feel free to pause the video at any point, especially if you've had enough of this voice. So here are the definitions. If you need to pause them. And here are the definitions of the rest. I think biodegradable and photodegradable are really important to actually talk about first. And biodegradable is something that's broken down naturally in the environment. So this is stuff where sort of, a bit of fetid water breaks it down, or photodegradable where light breaks down a polymer. So these are things that are really, really important because, as we know, those first polymers that were ever made, the man-made polymers, probably still exist in our environment. And any of you who have seen that David Attenborough's, I think it's Blue Planet, know that actually our oceans are absolutely full of these polymers. And it is, again, our legacy as an older generation to you is all messed up environment, viruses that sort of going out of control, and this this waste of polymers in the ocean. So hopefully it's something that you guys are going to have the challenge to sort out later on in life. And let's be honest, you're doing your A-levels now. By the time you go and do your degree, we're looking sort of 4 years down the line, you could be the person solving those problems. So it's important that we understand what those problems are. So essentially, polymerisation is just making big molecules from smaller ones. And there are two main types of polymerisation. We have our addition polymerisation, which is where we get small molecules, predominantly alkenes in this case, where they break open the double bond and they join together, forming a large chain. And that's an addition polymerisation process. A quick question for you: what is the atom economy of that process? What I'm hoping you're going to say is 100%, because the only product we get is the polymer. There are no other products, so definition of atom economy is the number of moles, or the mass of your, the formula mass of your desired product divided by the formula mass of all products. And because it's the only product, it means by definition it's going to be 100%. We talk about condensation polymers mostly next year during the second year. And the difference with those is we have molecules joining up in exactly the same way, but they always let out another molecule. So in this case, we've got water coming out. It can be something like hydrochloric acid. If you think about it, condensation is made from water. So actually, it makes sense that it's called condensation polymerization. Now, if we think about it, addition polymerization in this case has an atom economy of 100%. A condensation process will not be 100% because there is a second product coming out, albeit a useful product mainly. Now, addition polymers are mostly our man-made polymers, and of course we have lots of man-made polymers that are condensation polymers, but actually most biological polymers are condensation polymers. So think of your proteins, think of your DNA. They are all going to be condensation polymers. I would say DNA, definitely a condensation polymer. We have lots and lots of different monomers fitting together in different orders to make this really large molecule. Fantastic definition of polymerization. And all of them let out a small molecule as as the reaction proceeds. So, what is addition polymerization? So, if we look at it, if I have a small molecule such as this, and this is ethene, give me a moment, I will see if I can make my screen a little bit bigger with this one. So let's go, there we are, fantastic. So we've got ethene here. We can see ethene has this double bond. Ethene is unsaturated, and unsaturated means that the carbons do not have 4 bonds onto different things. You can see it's got a bond onto the hydrogen, a bond onto the other hydrogen. The carbon has a double bond, so it's carbon-carbon double bond, so it's unsaturated. Now, there was a German chemist back in 1898, I have to look at my crib sheet down there, his name was Hans von Pechmann, and he accidentally, whilst investigating diazomethane, which sounds like quite a dangerous chemical, he accidentally stumbled across this white stuff that was formed in his reaction. He didn't quite know what it was. He sort of left it alone. His colleagues characterized it, and they found it was just made of CH2 units joined together, and a CH2 next to a CH2 next to a CH2. And as they investigated it, they didn't really do much more with it. Then in 1933, a chap called Eric Fawcett and Reginald Gibson, who were working for the Imperial Chemical Industries, or ICI, based in Northwich, in our very own country, they were playing around with some chemicals at high pressure, and again they found this white sort of waxy material that was left behind. They were working with high pressures and high temperatures, and they found that this waxy material, just this residue was left behind. Didn't really do much with it, but then in 1935, a chap called Michael Perrin, he actually made a repeatable process for making this stuff, and hence addition polymerization was born. And as I said, it's really, really important, because if we look, my pen's made of it, my shirt's made of polymers, my watch is made of polymers, the chair I'm sitting on is made of polymers. And if you think about it, actually, if it weren't for those polymers, the world would be a very, very different place. So, how does it work? We have an ethene molecule, and if I break apart the ethene molecule, if I break that double bond, I can see that that can join on to another ethene molecule. So we now have 2 molecules together, and that's there. And what will happen is this now has a space for another ethene molecule to join onto it, and we end up with a longer molecule. If this just keeps going and going and going, thousands, upon thousands of times, tens of thousands, hundreds of thousands of times, we will end up with a really, really large chain. That chain is called a polymer, as in many. So poly means many. The single units for polymers are called monomers. So that mono means one. So if I put this back together, this is your monomer and this is your polymer. If it were much longer, I'll sort of hold it down here pretending it's a really, really long chain. It's not really. So really important you understand the difference between a monomer and a polymer. Now, they got this to happen at high temperatures and pressures. And as they did that at these high temperatures and pressures, they found that they could change the conditions and make things happen slightly differently and change the product or change the properties of the products they made. So they also discovered that there was a better way of making them. So technically this process will happen spontaneously at 200 degrees centigrade and at high pressures. However, if you use a catalyst, which of course lowers the activation energy, you can make it happen at a lower temperature. And in fact, they've changed the process so much that it can actually happen at a manageable pressure as well. So essentially, we could actually do this in the lab if we had the correct materials to do it with. I think the actual catalysts and things aren't particularly nice, so we wouldn't really want to, but it's pretty good. Now, polythene, as you can see, it's a really long carbon, single bond carbon, with the odd hydrogen carbon bond, and they are quite strong bonds. And because they're quite strong bonds, and because there's not much polarity on the chain, they are chemically inert. And when I say chemically inert, this means that they're not attacked readily by chemicals. Now, this is a really good thing when we're talking about actually making sure when you put your water in a bottle made of a polymer that it doesn't just dissolve and sort of fall apart. But when we're talking about actually its environmental impact, this is a problem because actually these things will not degrade in the environment. So this is going to be what our polymerization equation is going to look like. We have our monomer here, and this is the carbon-carbon double bond which the monomer is going to be based around. We have our groups here, W, Y, X and Z. They could be anything as long as we're based around this carbon-carbon double bond. We can see we have N of them, so we have a certain number of them. And then what we're doing is we are keeping the molecule in exactly the same orientation, keeping the groups in exactly the same orientation, and then making sure that we put a square bracket around it. That is a repeat unit, and we can see that there are N repeat units because it will take N monomers to make N repeat units of this polymer. My tip is always to make sure that you draw the carbon-carbon double bond in the middle of the picture, because then all you have to do is essentially draw a line coming from the carbon, a bond coming from the carbon going out of the bracket, a bond coming from the carbon and going out of the bracket, and keep everything where it is, maybe straighten those lines up, and you've made your repeat units. Okay, so this is some examples of some addition polymers. So this one here, we've got ethene, and we can see we orientate that carbon-carbon double bond in the middle, and our W, X, Y and Z groups are just hydrogens in this case, and we make this as our repeat unit. Notice they've used round brackets here. I would always say it's better to use square brackets, but that's just me, as long as actually the important bit, the bond going outside the brackets is there, it's no problem. That is of course polyethene. If you look here, we've got a propene molecule, and we've got a bit of a problem because the carbon-carbon single bond is going where our bond needs to be to get outside the carbon-carbon double bond, so to get outside our repeat unit. So what do? Well, actually, all we do is move. Oh, let's see if I can turn on some. There we go. Oh, it's not letting me do it. Okay, it's not letting me do it, so I'll just leave it. But essentially, we'll move this bond down here, and suddenly it means that we will have a CH3 group here. Our bonds go straight through here, and it means that we've made propene that's been polymerized, so its name is polypropene. We have this one here. This is chloroethene, and again, it's drawn quite nicely. All we do is draw a line out here and a line out here, and bang, we can make our repeating unit. And this one is polychloroethene. This is also known as PVC, or polyvinyl chloride. Really useful if you have windows with the frames made of plastic. You probably have UPVC frames, or unplasticized polyvinyl chloride. So this is what it's made from. The big problem with this stuff environmentally is this chlorine atom here in the molecule. And the big problem with that chlorine atom is the fact that if you burn polyvinyl chloride, if you try and heat it up too much, this will come off and it will make hydrogen chloride gas, which is, of course, what makes our acid. It's got the formula HCl, and if you breathe that in, it's not going to be very good for you. This one here, we have tetrafluoroethene. Any idea what it's going to make? Well, we draw the bond going out here, going out here. This is a really important polymer. It's very resistant to chemical attack, and if I tell you actually things cannot grip onto the surface of this, it is quite non-stick, can you guess what polymer it is? It is polytetrafluoroethene, also known as PTFE or Teflon. So if any of you cook with non-stick cookware, and if you don't like scrubbing things, I imagine you probably do use polytetrafluoroethene or PTFE or Teflon non-stick cookware, then actually you've used this polymer. So another thing that we need to do is to be able to spot the monomers. I'm just bearing in mind that I don't seem to be able to draw on this one, which is really annoying. But if you look, I have my carbon-carbon single bonds here. We turn the carbon-carbon single bonds into a double bond, and we can see that actually we could draw our square brackets there. This, whoa, we don't want to put the answers up right now. This would be our single unit, and this would be a molecule of ethene. This one here would have a single unit, which is a molecule of chloroethene. This one here would have a single unit, and we can see the single unit would be a molecule of propene. This is fluoroethene. This one here is a really interesting one. It's got this benzene ring here. This is called styrene, or phenylethene, which is probably its proper name. And this would be polystyrene. So those cups, those polystyrene cups that you have, this is one of those things. So often exam papers will ask you to draw repeat units. So I'm just going to show you a quick question which I found just today when I was looking on this subject. So if I just go to Chrome, I can see remote. I can see, oh, it's gone. Why is it gone? It's disappeared. No, I'll try that again. There we go. There it is. We can see this is a typical exam question that they'd ask. They have a cutout of a molecule. This is going to be a polymer. It's a section from a polymer, and it's unsaturated, made from unsaturated hydrocarbon, and it asks us to show one repeat unit of a polymer. So all I'm doing in exactly the same way is just going, okay, there it is, just there, and there it is, just there. We can see that we have just got this point here where we have the carbon-carbon double bond going there, and then coming off from this carbon we'd have an ethyl group. From this one we would have a methyl group, and that is our hydrocarbon that we have. It's not allowing me to draw on here, which is really annoying, but it would be, let's have a quick look, it would be ethyl, no, actually it would be 1, 2, 3, 4, 5, it would be pent-2ene would be the monomer that makes this. And we can double check that that is the case. Thank goodness that's the case, otherwise that could have been very embarrassing. So this is what it would look like. So back to the PowerPoint. So remember when we're drawing our, oh dear, it all seems to have gone wrong. When we're drawing our repeat units, we are going across a single carbon-carbon bond. So we're going for a single carbon-carbon bond. They bond together and make a carbon-carbon double bond. Our monomer here is going to be chloroethene. So this is quite an important thing. If I have propene bonding together, you can see in this sort of animation that all that's happening is that the double bonds are opening up and they're joining together. But nature is not always this friendly. What we might find is that actually this methyl group will be here, this methyl group will be here, this one will be here, and it can be quite sort of random, and this will affect the properties of the polymer. It will affect its density, its strength, what temperature it melts at and things like that, its resistance to attack. So it's really important we can control these. And we can do that using the chemistry, using the conditions in which we create that polymer. And it's really important to know that they can be varied. So here are some examples of polymers. We have polystyrene. Polystyrene is really interesting one. It's very insulating if you mix it with air. And in fact, if you get a polystyrene cup or something like that, you will find that actually most of a polystyrene cup is air. You can dissolve it in acetone with absolutely no problems, and it will make a minuscule amount of polystyrene. Funnily enough, because of that, polystyrene is not widely recycled because it's not worth having trucks driving around working to recycle a load of air. We've got polypropene here, very strong polymer. It's used in food packaging, fibres in carpets. It's so strong it's used for ropes. Polyethylene, very widely used. It's our sort of first real man-made polymer, and it's used in lots and lots of applications. But because it's used in all these are things that actually are persisting in the environment. So grocery bags, bottles, sort of water bottles and things. So if you look on your water bottle or whatever bottle, you will see that you have these different signs on there, 1, 2, 3, 4, 5, 6, 7. And this tells you what type of polymer that you have. And it's really important they have these, because if you were going to recycle poor Pete over here, or PETE, I think, not entirely sure which one that is, that's I'll find out later, that one, LDPE, low density polyethylene, we can see you only want to recycle each different polymer with other parts of that polymer, and the reason is because if you start mixing them, they could have very strange chemical properties. There we are. PET is polyethylene terephthalate, a really interesting one. It's used a lot for frozen meals, etc. I say this one is the one that you really have to make sure is not mixed up with anything else, because as soon as you heat it up, it decomposes and makes some hydrogen chloride gas, which is really not very nice. So if you have a look in the textbook and look in the page 40, you can actually sort of fill in the summary sheet, which will help you understand all of the different properties of those polymers. So have a quick look at that. these are some of the answers with that sheet. Now, this is one of the big problems with addition polymers, and I spoke to you about it earlier, and I sort of mentioned David Attenborough's blue planet, and we can see here we've got, it looks like, is that coconut? That's not plastic, but we've got lots and lots and lots of bits of plastic which are just turning up in the sea, and there's a couple of massive oceanic sort of islands made just of plastic. We're finding that plastic's turning up in the marine life and things. It's really not very nice. And the big problem is that actually our plastic is not breaking down chemically. It's breaking down mechanically, which means that we're getting these tiny microparticles and nanoparticles of plastics, and they are going into our food chains. They are essentially messing up the planet. So we need to have a more intelligent way of making polymers. So the big problem with disposing of these things is the fact that they persist in the environment. And because they persist in the environment, they can cause harm to wildlife. They can contain some horrible metal ions, lead and other horrible things that are used in catalysts. Some of the polymers are very difficult to recycle. So, for example, I mentioned PVC, that as soon as you start heating it up, toxic gas is given off. If we look at something like polystyrene, they don't tend to recycle it because most of it's air, so actually they don't get much money for recycling it. So it's really bad, but they can recycle most polymers. You can also burn polymers as a fuel to generate electricity, and yeah, it works pretty well. We have a plant in Gloucestershire which is currently burning rubbish, and I imagine that actually they are using the rubbish, and quite a lot of what they're burning is probably polymers because they're not sort of well separated out. Something else that we can do with polymers is to make it into a chemical feedstock, so we can use it to make other chemicals with, and it's really important. This is one of the types of recycling that they require you to know about in the exam. So what are the stages of recycling? What happens? Well, the first thing is they have to sort them by type. So those numbers on there, you will find that every type of polymer has its own different chemical signature, and it will whiz past the machine which shines a piece of light down it, and it sort of works out what type of polymer it is. That puts it then stacks up the different types of polymers together to make sure that you're not mixing polymers. It chops them up into flakes, it removes any impurities, then it makes and remolds things. So it's a really nice process, but it is quite an energy intensive process. So maybe we would want to sort of use them in that way. Maybe there's a better way. There are other things that are starting to be used, and they are things like cornstarch, polymers derived from potatoes, etc., polylactic acid drink cups. So these are things that are made from biological materials, and because they're made from those biological materials, actually they're biodegradable, and they can be made more sustainably. The only thing is, it does still require energy to make them, and if you're growing plants to make polymers, you're taking up land which could be used to grow to feed our ever-increasing population. So you've just got to sort of think of those sorts of things. So if we look, the packaging from here is made from polylactic acid. The only thing I would say, if you're using something like PLA or other materials, actually it's going to break down more quickly and it may contaminate the food. So you've got to be really careful in how things are packaged, and there is a lot of research going on in this area at the moment. So, talking about biodegradable things, now bioplastics, they're hopefully made by less hazardous processes, and the whole idea is that over time bacteria can get in and start breaking down the plastics. We don't want it to happen instantly, because if it happens instantly, you take your coffee away with you and it breaks down and it goes everywhere. We don't want that. We're talking about over a few years rather than over centuries of things breaking down. So really important area, and it's something that's getting bigger and bigger, and there's lots and lots of research into it at the moment. The big problem with the alternatives is that they are actually quite expensive to produce. They're not particularly durable, and they can just come apart, so they're less predictable. So if you're packaging food in something that actually is quite biodegradable, then you have to worry about the packaging as well as the food inside the packaging. The other thing is you still require to put energy in to make these polymers. So maybe we should think of some form of alternative. Who knows? And the other big thing is the fact that, I said it earlier, if we're using land to grow crops to make these polymers, we're not feeding the world with that land. Right, here's the work to do. Have a quick read for yourself about polymers. Have a quick look at the questions that I've listed. I will pop this in the comments section on YouTube, or you can just pause it here if you need that. Thank you very much for listening.